Bismillahirrahmanirrahim. Welcome to Easy Learn. This is Diode and Application Season 2. Okay, first of all, we recap about the last episode. We had discussed about the breakdown characteristics of a Zener diode and also discussed about how it regulates the voltage. How it is used as a voltage regulator, and now in today's topic, I will discuss about the Zener equivalent circuit. I will focus on Zener equivalent circuit, means to say the thing that we discussed last time, the graph that is basically characteristic curve, and I will draw a how to use this characteristic curve when we are talking about the practical case, or we are talking about in circuits. That is basically the equivalent circuit of the theoretical work of the equivalent circuit of the just theory. Okay, there are two types in the equivalent circuit. When we talk about the equivalent circuit of Zener diode, we have two types. When we talk about the general diode, for example 1 and 4007, that operates in the forward bias state normally, and so that operates in normal diode. There are three states that are an ideal model approximation, that is number 2 practical, and third one is complete diode approximation. While in this case I will discuss only two, that is number 1 ideal case approximation, you have to focus about two things, that is number 1 ideal case, not actual, and second thing is it is approximation. So the actual case basically is a little bit different about the approximation, so that's why we also discuss the practical case. This is just ideal case. So why discuss about the ideal case if it's not correct, or you can say even it's not 100% correct or partially correct. So it's basically just for building a concept, because number one thing is it's easier for understanding. Number one, it is easier, and second thing right now is important, troubleshooting, and troubleshooting is also very easier in the case okay, troubleshooting. So for most circuits analyzing, it's easier, number one, and number two, its troubleshooting work is easier to learn, and for learning purpose and for understanding concepts, it's easier, it's simple, as we are just as it, for example, when we for example, like a book, first of all basic concepts, then the book continue towards the higher concepts, and after building the basics of something. As I am creating a series, I'm making a video series, I just start about the Zener's introduction, and now I'm coming a little bit upward, just like that. So it's easier to learn, and number two is easier to work. The ideal model will give a very good results, as in much cases to use than more complicated models. So when a Zener diode is operating normally, it will be in reverse breakdown region, as you know already better. So first talk about the Zener diode. Let's start, and first of all I am drawing the symbol. As you know, the symbol is just a stylish Z. This is the symbol. So now this basically bubble shows that it's not right now connected in the circuit, nothing else. Okay, the approximate circuit for this is basically can be drawn here. The first approximation of the Zener diode reverse breakdown is ideal, so it has a constant voltage drop. So this is the basically graph. In the forward, this is the voltage side, and this is the current. This is the forward current, forward voltage. This is the reverse, and I reverse. So in case of the in case we are talking about the forward, this is the when I have another color. Okay, this is overlapping this. Maybe you cannot see this color, but I'm showing with the arrow. Okay, these when it's forward bias, I'm not, we have no concern with the forward bias because our diode is will operate in this region, reverse bias. So when we are in reverse bias case, there are no voltage drop because we are now in the ideal case. So in reverse bias, this looks like this. No voltage drop, and totally voltage is receiving no resistance of current right now. But when there is a knee away of this curve is here like this straight, after knee this there is no voltage available, and it's totally regulated voltage. For example, if it is 5 volts, so 5 volt regulator will give 100% 5 volt, no change, even if current is changed. But from I is Z knee, this is what is this is I Z knee that we had discussed in the previous videos, and this is I Z maximum current, Zener maximum current, this is Zener minimum current. So if we change from bottom toward upper side, minimum to maximum or maximum to minimum, there is no change in the current. As you can see, there is a straight line, so we can represent its equivalent circuit. So we are talking about the equivalent circuits. So we can basically, it has a constant voltage drops where, and this is a constant voltage drop, no variation in the drops. It's a still a stable voltage drop. So it's a nominal Zener voltage. We are obtaining this constant voltage drop across a Zener diode produced by the reverse breakdown is represented by a DC voltage symbol, and that is in the reverse, that is connected in the reverse bias. Because this is anode, but I am showing here at the anode side this is negative and this is cathode, and I represent this side with the positive. If you remember, I represent in the normal diode case the reverse of this, polarities are reverse in that case. But right now the voltage of the battery here, it has a positive on the cathode side and negative on the anode side, because you know the Zener diode operate on the in the negative region, so that's why its these polarities are reversed. Now, there is a very important thing right now, that although Zener diode basically is not does not produce any voltage, but we represent it with the voltage as we represent it by the simple diode. In simple diodes case, basically the if it's a 5 volt regulator, for example we talk about this case, so it's a let's say 5 volt regulator. So if we show it with the help of a reverse polarity battery, we mean to say that we are obtaining a constant 5 volt in graph of this battery. This is the graph, and it is a constant graph of 5 volt. So we say that but its polarity are in reverse polarity, so we are obtaining this graph here in contrary with this. If with this its polarity will be different, then definitely graph will be on the right half side. So that's basically just for understanding. Either it's not actual or just for better learning, we can say that this is the this is parallel circuit or a equivalent circuit of the Zener diode. If it is a 10 volt regulator, we represent it with 10 volt, and we assume that 10 volts are already available. Although battery cannot provide 10 volts, this is another question arise, but we assume that basically this is just based on the assumption model totally, and that is the regulated voltage. We can say, for example, 5 volt, this is the VZ in this case. So now the second important one is that is the practical. This is the practical model. Although it's not 100% complete right now, and it is also approximation, but it includes, in this case we include the resistance is included. So when resistance is included, basically we mean to say that internal resistance and we mean to say that impedance is included. So impedance is represented by Z, and in case of the Zener, small z is used in the subscription. And it is when we are talking about the practical case, the Zener diode, the Zener impedance resistance is added in this series with the One more thing right now, this is the linear resistance and constant linear, constant linear resistance means to say its value is constant, as I already explained in the introduction to electronic series in details about the resistance, linear resistance, non-linear, and this is the linear resistance. If it continue with the same pattern as in this case, sorry, here no resistance, I'm talking about just this case. If at this point this is 5, it's continue. If I at 1 it is 5, at point 2 it will definitely 10, and it will continue in the same pattern, it will not change. For if this is the basically ideal cases, or you can say that just approximations. And if this is ideal case, sorry, I just again draw the ideal case. If this graph changes, for example this like temperature graph, etc., then at this point let's say 5, at this point second point let's say it's 15, so graph is changing. We cannot decide by just 2 points, by after analyzing or sampling just 2 points or 3 points, that the resistance will go in the same pattern. But right now, for simplicity in practical model approximation, we consider that our model has a constant resistance. So okay, first draw about the I'm not have any concern with this side, forward side, just talking about the reverse side. This is VR, this is IR, current reverse bias. Let's say this is our small leakage current, but after the knee, when this is the knee portion, let's say this is after the knee portion, this we had received this graph. So this is our knee point. This point is called IZ knee point, and this is our maximum point, IZ maximum. So these 2 points are available for us. So the actual voltage curve is not ideally vertical, so like this case, that's why a little bit a bend is available right now in this curve, a little bit just at an angle it's bent, while it's almost 90 degree with the horizontal axis, because it's a practical case. We added linear resistance, so it's equivalent circuit. First of all, let's talk about the equivalent circuits. Again, I draw the symbol. This is anode, this is cathode, and it's equivalent circuit. Right now here a resistance is added, and in series with the same, the ideal a battery. This is the positive and this is negative, while this is the resistance and this is called impedance, and small z for Zener's impedance, and this is shown in the form of block. While for this we can say that this is positive overall and this is negative at the cascaded circuit. Okay, and if we talk about, for example, if this is since the actual voltage curve is not ideally vertical and change in the Zener current basically, so if I take 2 points, for example this is 1 point, so I take a sample of 2 points, for example 2 points, I change this is the current axis now, or this is the current is changing on the downward and voltage is changing in the horizontal axis, this is vertical axis. So I take 2 points, this is point 1, or you can say this is point 2. This is basically IZ, as I told you in the previous episode, this is current. So this is IZ1 or IZ2, and their change is basically represented by delta IZ generally. Okay, delta IZ, what is delta IZ? That is I2 minus I1. Same is the case, the corresponding voltage is this. I receive here this first of all I show this graph with a shaded portion so that it's easier for understanding. No, okay, this is a change here in the voltage that is represented by V1 or V2, for IZ1 is VZ1, this is VZ2. This point, when by using this point we receive the voltage, regulated voltage, that is VZ1, and by using this point we receive another point, that is VZ2. So what is delta VZ is basically VZ2 minus VZ1, as like in this case. So basically we had received 2 points. What is the basically meaning of the regulation? Regulation is basically mean that if we change these point horizontal axis, in vertical axis, if we whatever the points, for example we change these points, our purpose of the regulation is if for example these points are changed but we need a constant voltage. If we receive a constant voltage, the narrow the variation is, we means our Zener diode is better. It has a better regulation. So for example, if 2 points right now change, you can see this is a change, and we also receive a little bit change in our voltage here in this case. So what is the formula for this, its impedance changing in the resistance? This is because of this graph. If this graph is like this, for example this graph, then the points, if you imagine right now, these points will be more the better regulation. If this graph will go more steeper, then what happens, the graph will looks like more closer. So the angle, for example, is towards 90 degree, or this, when this curve will looks like a straight curve on the downside, better the regulation is, it shows the better regulation. So this curve basically depends upon the resistance. If the resistance is basically low, it shows a better regulation. So resistance is basically Z, in this case impedance. So we want a formula basically that is derived from the Ohm's law. What Ohm's law say? Ohm's law said V is equals to IR, as I explained in Introduction to Electronics Season 3. V is equals to IR. Here in this case we need this R. R is equals to V over I, and you know R is, what is R? That is impedance. In this case Z is equals to V over I, and V is basically delta V Z, and for Zener, and for I, what is I? Delta IZ, delta IZ, sorry, what I am doing right now. This is basically our now graph, formula. This is the formula. Normally delta Z is specified on a Zener test current. Okay, this is this what is this basically? IZ, I told you, that is IZ is Zener test current. We are basically testing, we are by taking the 2 points. So I will also talk I will also give you an example. First solve an example. With the help of an example you understand better in the next episode, because already I taken the time of almost 2 episodes in this episode, because this is important topic. So I want to teach you with by taking some your precious time as well, but this topic is important, that's why I take your time. But now if you learn this topic, I hope in the next example you might found very useful and easier. So next time we will talk about an example regarding this one. And one more important point I want to tell you right here, in most of the cases you can assume that this point where is the Zener resistance? This resistance right now is the small constant over a full or entire range. But right now it's important point right now I missed, I'm going to miss, but right now the point is, it is best to avoid the operating in this region. It is best to avoid operating a Zener diode near the knee. Where? Near the knee, because the impedance basically changes dramatically in that area. You know, the resistance are changing very fast right now in this area, so it is better to operate in this lower bottom side or upper side for in case of current in this region, because here the resistance is changing quite fastly, or you can say that dramatically change in the change can be seen right now. That resistance basically in case of current, you can say that the current basically is not increasing, just leakage. And here you can see suddenly the current is increasing, resistance is reducing, and push of the current is increasing. So here if we operate in this region closer to the IZK, if we take samples, so it may be our sample value may go to closer to the knee and our point, or maybe we calculated the wrong value. So it's better to take value or operate your Zener up from the lower value. Okay, take care, see you next time. Watch and grow.